Yeah, doing an intro.
No need lah. Ayo, at this point, they know what's up. You know.
Nice. Okay.
At some point, I want to figure out nicer colors. I feel like these colors are not it, man. Actually, maybe this one. That looks kind of cute, right? I guess we'll use that.
Yeah.
Maybe this one I'll put this one, and then this one I'll put this one. Okay, hopefully that's legible. We will see. I feel like the color is too dark. I feel like it's depressing me. Like I see, I'm like, oh, it's so sad. The blue is like so blue, like depressing blue. Okay. The next technique that we're gonna show you is the proof by contradiction technique. Okay, so it's gonna be a bit unintuitive, so bear with us. Okay, but the general idea of a proof by contradiction, it kind of follows this pattern. What we're going to try to do is we're going to try to assume. Oh, sorry, let's not assume. The general idea, right, is that we're going to try to assume. Which one is it again? Do we assume P or do we assume not P?
Not P.
Okay, so we're gonna assume not P. And eventually down the road, we're gonna derive a contradiction. And if you remember from the previous week, to derive a contradiction, we're gonna use the symbol, the not symbol. Okay. And at some point, if we ever create this symbol, we're going to conclude that P must be true. Conclude. Okay. So it's kind of like you want to assume an absurd situation, right? So in other words, you're going to assume something and you're going to eventually create a really crazy scenario that cannot happen, like a contradictory scenario. And from there, you will be able to conclude that, oh, the only way this is possible is if we are, like our assumption was wrong. That's kind of the idea. It's this proof technique is really the source of a lot of confusion, right? So the blue is not good. I'm going to go back to the original blue. So what I'm going to say is that we like try to pay attention to what we're trying to do here, and I've built the proof system rules so that we're a bit more careful with it, right? So in other words, a lot of students, at least for the other degree, the CS degree, they all almost always make mistakes like in this area. So if any of the CS students are watching this video, please stop making mistakes. Like
You're just straight up flaming them in this point.
I'm straight up flaming them. You all do it way too often, and you need to do better. You need to do better. Okay, like so in my proof system, hopefully we will avoid that. We will hopefully, very very hopefully, avoid that. In other words, right, stick to the derivation rules that we gave you. You should be fine. Okay, so let me show you what I mean. Okay, we're gonna try to prove this statement. So what's this statement saying? This statement is saying for all. Oh, wait, hold on. This is we need to change this. This is faulty. Dun dun dun. Is it faulty? It is faulty. No, it's not faulty. It's not faulty. This is saying for all integers. Okay, for all, intuitively, what it's trying to say is that if you go through every possible value of n and go through every AB, okay, if you can factor n into a times b, so in other words, any possible factoring of a times b, okay, it must be the case that either a is less than square root n, less than or equal to square root n, or b is less than or equal to square root n. So let's go through some examples, right? Let's say it's like 25. Okay, so 25 can only be written one of two ways, I think. It can only be written as either 1 times 25, or it can be written as 5 times 25.
Sorry. 5 times 5.
Yeah, 5 times 5. University level, guy cannot do, has 2 degrees.
This is not a course about calculations, and
it's not a course about calculation. Yeah. The worse your prof is at calculation, the better he is at math, I will say. Okay, actually I can't say that. My PhD supervisor is very good at these things. But not because he's a mathematician. Anyway, right? So what we're trying to say is that no matter the way that you factor it, right? In other words, all possible ways to factor 25, there will be at least one number that is less than or equal to square root of 25, which happens to be 5, right? So the first way of factoring it, right? Okay, 1, that's less than or equal to square root of 25. The second way of factoring it, 5, that's less than or equal to square root of 25. It's not possible to find a number with a factoring, like, every number every factoring of every number must satisfy this relationship. Some of you might have, especially from my class, might have already heard why we actually use this in computer science. But we'll talk about that later. Yes, something like this is actually useful in computer science, believe it or not. Actually useful. Okay. So here's what we're gonna do. To do proof by contradiction. So I'm still going to start off with the usual let n be from z, arbitrarily chosen. This part here is nothing to do with proof by contradiction. It's just, I need to prove a for all, right? So I'm actually just going to let n be from z, arbitrarily chosen. I also need to let a and b also be from z, arbitrarily chosen. So let me do that now.
Can you just intro all of them in the same line?
You can now. But I'm just gonna write it separately just because, like I'll go through the tedium. It's not too hard for me because I'm copy pasting. But if they want to write it all in the same line, I think I'll accept that. We don't have to be too formal. Yeah, but I'm guessing in Lean you have to write them separately. Do you?
Not really. You can just intro and then like
Oh, you
NAB.
can.
Yeah.
Oh, that's quite nice. Okay. Yeah, we can do it all on the same line if you want to. But yeah. Okay. So
Okay.
So let's keep going, right? So what we now need to do is we kind of need to say, assuming that n is equal to a times b, right? We now need to conclude this thing. A is less than or equal to n, or b is equal to square root n. So the next line of my proof, I'm still gonna do this. I'm still gonna assume n is equals to a times b.
It's like whenever you have an implication, you just assume the front part by default.
Yeah. Except if you remember from the end of the previous video, we kind of had to do the opposite, right? We had to do the contraposition, right? How do you tell which one you're supposed to do? Watch the next video and we'll tell you. Wow, I'm starting to sound like a YouTuber. Like these things are like suddenly like coming to me automatically. Anyway, let's keep going. So here is the crux of what I'm going to do. Okay, what I'm going to do is I'm going to make one more assumption here. I'm going to assume that it is not the case that a is less than or equals to n, or b is less than or equals to square root n. Okay, so if you haven't caught on yet, where's my highlighter? If you haven't caught on yet, I'm taking this thing. Well, the highlighter is atrocious. I really can't use it. I'm taking this thing and I'm negating it. The thing that I want to prove, right? I'm gonna negate it. So literally take the whole thing, copy paste it, negate it. Okay, why are we doing this? It's kind of weird, but let's keep going. So we know from the previous week's tutorial, right, that not P or Q is equivalent to not P or not P and not Q, right? So I'm gonna write not a less than or equals to square root n, and not b less than or equals to square root n. Okay. By the way, right, just a quick reminder, everything here was let, so no justification needed. There's an assumption here, no justification needed. Assumption here, no justification needed. This line, however, is not an assumption, and we're not drawing a variable from a domain. So what must we need for this line?
Logical equivalence.
Yeah, so we need a justification, right, which happens to be logical equivalence. Yes. Right. Okay, good. So let's keep going then. So I'm just gonna say that like this is we're gonna say it's acceptable in TCX1004. In some math modules it's not acceptable, but in TCX1004 this is acceptable. I'm gonna rewrite this. If a is not less than or equals to square root n, it must be the case that a is bigger than square root n. Oh wait, so I said square root n, I wrote n. Something is really
Oops.
off with me today. A is bigger than square root n, and b is bigger than square b is bigger than square root n. Okay. Okay. Yeah. Do we call this logical equivalence? I guess we would call this like basic algebra, right? Because this feels like a statement about algebra. You know what I mean?
Okay.
Okay. So let's think about what happens here. So a is larger than square root n, and b is larger than square root n. Okay. So what can we say about a times b?
It's bigger than square root n times square root n.
is bigger than square root n
Yeah, just kind of
times square
combining
root n.
the
Yes.
yeah.
Okay. So a times b is bigger than square root n times square root n, which by the way, this side is equals to n.
N. Yeah.
Okay. So let's think about what this means. Okay. So a times b is now bigger than n. Okay. Since a times b is bigger than n, I think it's very safe to say it is not the case that a times b is equals to n. Right. So I guess we will call this basic algebra. I think that's fair to say.
Okay.
Right. Now there's a reason why I wrote it in this form. There's a reason why I wrote a not here. There's a very specific reason why. So I'm going to copy paste this line. I'm going to say not AB equals to N and AB is equals to N. Okay, so I'm taking this line. I'm copy pasting it. I'm also taking this line and I'm copy pasting it. So which rule are we using?
Let's see. So you introduce a conjunction, right? So
yes, so it's the conjunction rule. So conjunction rule on lines 4 and 4.6.
4.5. Okay.
Yeah, 4.5. Oh my god,
it's okay. I got this.
Yeah. Okay, so we now are saying that a times b is not equals to n, or but it, to be very, very precise, we're saying that it is not the case that a times b is equals to n. And at the same time, we are also saying that a times b is equals to n. How can like that? This is not allowed, right? So what's going to happen here is really what the whole point of this whole special, like we specially had to carve this out into one video. We are now able to write the bot symbol. Okay, so this is the contradiction rule. The contradiction rule states that if you have some proposition or some statement, I don't know what you want to call it. Let's not call it a proposition. Let's call it a statement like P. Okay, so a statement like P, and you also have a statement not P, and you add the two of them together. Okay, so what I'm saying is that basically you have literally written down something like P and not P, or maybe not P and P, whichever way. I am not fast in this module. Some people are fast, but I'm not fast in this module. Right? You can use the contradiction rule to create this thing. This is called the bot symbol, or you can think of this as just saying contradiction. Okay. So we've derived the contradiction. So we need to pair the symbol. So I'm gonna mention this now. This symbol can now get paired with the assumption that led to it. This was my assumption. I hope the plosive on my mic wasn't too harsh, but this assumption that we made, okay, is paired with this contradiction. So what is going to happen now? Is that via the contradiction rule, the proof by contradiction rule, we can literally copy paste this thing without the negation. So I'm going to copy paste it now. A less than or equals to square root n, or b less than or equals to square root n. Okay, so this is the proof by contradiction rule. Okay, you need to take the assumption, so that's line 4.1. You need to take the contradiction symbol, that's line 4.7. Okay, so on lines 4.1 and 4.7, we can combine it to create this conclusion. Okay, now everything else is clean up. We've arrived at our desired conclusion. We've arrived at the conclusion that either factor is less than or equals to square root n. Okay, so all that's left for us to do is to pretty much say, okay, this must mean that for all b in z, right, a is less than or equals to square root n, or b is less than or equals to square root n. Okay, this is universal generalization, right? Then now we can say for all a in z, a is less than or equals to square root n, or b is less than or equals to square root n, right? And can keep going. So then we can say for all n in z. Oh wait, hold on.
Wait, I don't get what you're writing.
Yeah. I just realized I skipped a lot of rules, right? Like I wrote it down and we didn't even check whether the rules were correct in the first place, right?
Yeah.
So see, nearly got scammed, and then I was like, cannot be allowed, right? So we're not actually doing that yet, right? So what we need to do is check what assumptions we made, right? So we made an assumption. We have to clean it up, right? So we made this assumption on line 4 that n is equals to ab, right? So on line 6, I made a mistake. On line 6, what we have to do is instead first say n, assuming that n is equals to a times b, then a is less than or equals to square root n, or b is less than or equals to square root n.
Mm-hmm.
So now we remove the assumption. We remove the assumption. We use the implication introduction rule, and then now we can do the copy pasting, right? So take
Yeah.
take the conclusion that you made, right? Paste it, and we can write for all b in z. This line 7. Okay. Now we're using universal generalization, right? Take this line, copy paste it. I guess I need some space on the right, so I'll shift this further to the right.
Yeah.
So you can say for all a in z. Okay. And then I'm gonna copy paste this again. Paste it here. A bit more space. For all. Oh, I didn't copy paste the a. For all a and z. And last one, right? For all n and z. This is line 9. Right? So for all n and z, for all a and z, for all b and z, if n can be factored as a times b, then either a is less than or equal to square root n, or b is less than or equal to square root n. This is how you do proof by contradiction. Right? So we arrived at the original statement that we wish to prove, which happens to be this one. Again, if you're curious why this is important in computer science, why this is actually helpful, like we will record a short snippet explaining why. But for now, like, take my word for it. Trust me, bro. For another half hour or so, actually more than half hour, but half hour or so, that this is actually useful. We actually do use this. I'll show you why we use it, but not in this video. Okay, does that make sense?
Yeah. It's just super tedious to even get the contradiction because you need to introduce
directly
the
create the
conjecture.
thing, right? Yeah.
Yeah.
But this, I feel like this is the most foolproof way, because I think if I don't enforce, at least for me, the rationale on why I'm doing this is that if I don't enforce that people, not just students but anyone in general, right? If they don't literally write P and not P, there is a chance that they're skipping a few steps in between, and then they'll just say, "Oh, contradiction," even if there isn't one. Or sometimes what's going to happen is that they'll create a bunch of random statements, and then they'll just say, "Oh, this one contradicts that statement," and I'm like, "Yeah, but your statements came out of nowhere." You know what I mean? And that's not very good. So I'm trying to keep it this way to prevent those kind of errors from happening. Right? Remember how I started this video by saying the normal undergrad CS cohort, all of them are very error prone, like, and they need to do better. I think this is part of it. I really think this is part of it. I know I'm flaming the CS students, but I think in our CS discrete math course, right, the fact that they don't have a system like this really annoys me. It really annoys me. Like, the fact that we somehow cannot give this to them. I don't know why. We're not allowed to give this to them. Like, it's brain damage, It's actually brain damage to not give this to them, I think. Right? Very strong opinions recorded down on a YouTube video, but I really think, I really feel that way. Yeah. Okay, so let's do one more proof for the road, I guess. For the road, I suppose for the road.
The hard one.
The hard one.
It's not that hard.
It's pretty hard. So we're gonna try to prove that square root of 2 is an irrational number. Okay, so in other words, right, we want to prove. Let me write this down. Where's the pen here? Pen here. We want to prove that square root of 2 cannot be written as a fraction, basically. Okay, so just to be clear, to give you a little bit of background, okay, this set, right, the set of rational numbers, I asked my students in the tutorial, and they said that they learned it from the other module, linear algebra. I think linear algebra.
Calculus. Yeah. Oh, actually, the course is together, right? Calculus and linear algebra for computing.
Okay, I see.
Yeah.
Okay, very weird. But just to be clear, right, mathematically speaking, if a number is a rational number, this means that x can be written in the following way: a divided by b, okay, where b is non-zero and a is an integer and b is an integer. Okay, so this is just the definition of rational numbers. The definition of rational numbers. Okay, so to claim the square root of 2 is an irrational number is to claim that 2 is not in set of Q. In other words, it means that it should be impossible for us to write square root of 2 as a divided by b, right? Where b is non-zero and a is an integer and b is an integer. Like this is not possible. Well, the entire thing is not possible. Does that make sense?
I need a bit longer to parse the thing.
Sure.
Yeah, yes.
Right? Okay,
I think it's an N, right?
Yeah, it's an yeah, so it's an N. Sometimes I use commas, but it's an N, yes. Okay, so we're gonna use a few helpful lemmas. I know they look super intimidating. I'll read them back to you in English, right? In fact, right, this one we kind of proved it, right? So no excuses here. We know what we should all know what this is. Okay. Okay, so we want to prove that square root of 2 is an irrational number. I don't know many proofs, any like alternative ways to prove this. Actually, I think this is like the only way that I know how to do it. Okay, before I even talk about lemma 2, let me give you a proof sketch. Let me give you a proof sketch, right? So I'm gonna sound very salty for a bit, but this is how our CS students, I don't know why, are taught to prove this way. And to me, it's so sad, okay? Like, to me, it's so sad. Okay, so here's the proof, right? So what they'll do is they'll say, okay, we're gonna assume is the green color okay?
Maybe
Is
something
it too
darker.
like something darker? Okay.
Yeah.
We'll go back to the depressing green. We're gonna assume that square root 2 is rational. Okay. So then they will say, okay, this means that square root 2 is equals to a over b, where b is not equals to 0, and a is an integer, and a is an integer and b is an integer. Okay. And then they will say something along the lines of a over b can be written as a simplified fraction. So simplified fraction here means it's like the smallest possible terms already. You can't make them any smaller. Okay. And what's going to happen now is that then they'll say, okay, well, this means that I can square both sides and multiply b across. So I'm going to write this as 2 times b squared is equals to a squared. Okay. And then what they'll say is that, well, this means therefore a squared is even. Okay. And because a squared is even, we're going to apply this lemma that we proved in the previous video. Right? So because a squared is even, we now say that a is even. Okay. Well, a is even, which means a can be written as 2t. Right? And then they'll keep going and then they'll say, this means that basically 2b squared is equals to 2 times 2t squared. This is basic algebra. Right? And then after that, what they will say is that, okay, this means that b squared is equals to 2t squared. Okay. And then they'll say, therefore, this means that b squared is even. Okay. Then surprise, surprise, we're going to do the same thing again, right? So now, because b squared is even, this means therefore b is even. Right? So now I can say that this means that b is equals to 2 times, let's use something else, q. Okay. So originally, what we had, right, was that root 2 is equals to a over b. And now we know this means that it's equals to 2t. divided by 2q. And then we will conclude by saying, but this is not simplified. Right? And then they'll say contradiction. And then from there, they will say, therefore, square root of 2 is irrational. This would be the whole proof. This is what they would write. This is how our CS undergrads write proofs. I sigh of disapproval. I don't approve. I don't approve. I know I'm not even kidding, by the way. I actually really don't approve of this. I really wish we could give them a lot more formal things. Yeah. But yeah, this is still a proof sketch. I will call this a proof sketch. It's a proof idea, right? It's an idea of how you should do things. But it's not a proof. Right? I don't know. So shall we see the real proof? Unless you want to comment on this.
Nah.
trying to make sure you don't burn any bridges like me, right? Flaming the CS cohort full time. Oh yeah, okay. Let's keep going. Let's keep going. Hey, but I'm pretty sure my students from CS will agree. They'll probably like, yeah, Elton is right. I really hope. Anyway, let's see. Okay, so this lemma, like we proved it in the previous video, so I'm not gonna go through this, but let me try to explain what lemma 2 is morally trying to say. What lemma 2 is morally trying to say. Lemma 2 is saying that if we went through every possible rational number, for any rational number, it doesn't matter which, give me any rational number. Okay, you can find two values p and q. You can find two values p and q for which, like, okay, ignore this d for now. Okay, what we're going to say is that for any rational number, x can be written in a fraction form, p over q. Okay, and the same thing as before, the denominator has to be non-negative. So we're going to say it can be written in a way where q is non-zero. Okay, and what we're going to say is that if we go through all possible divisors, d, okay, if d divides p and d divides q, then d must be equals to 1. Okay, so what is this trying to say? It's basically just trying to say that x can be written in simplified form. Right? So in particular, we are just saying that a rational number can be written in a simplified fraction. This is the mathematical way to write it down. Does this make sense? So reading this back in English, right, it's just saying that for any rational number, there is a way to write it in simplified fraction form. Right? So P and Q is your simplified fraction. How do you argue that it's simplified? You argue it's simplified by saying, go through any integer. If any integer divides the both of them, the only possible integer that divides the both of them is 1. That's a simplified fraction. Like 5 and 7, right? For example, 5 out of 7. The only possible integer that divides these two is 1. So this is a simplified fraction. Right? On the other hand, if I gave you something like 10 and 20, is this a simplified fraction?
No.
Because you have a common divisor of 2, right? 2 divides 10, 2 also divides 20. Does that make sense?
Yeah, you can also divide by 10. Yeah.
Yeah, oh yeah, okay. And also divide by 10. Yes. You only need one.
Just anything. Yeah.
Anything, yes. Right? Or like, I guess, like, 6 and what other number is that? 6 and 10, I guess. Both 2 divides both of them. Anything along those lines. Right? Okay, so really all lemma 2 is trying to say mathematically, if you read it back morally speaking, it's just saying that any rational number, any number in the set Q can be written as a simplified fraction. That's really all it's trying to say. Okay, so we're going to try to do this proof. We're going to try to do this proof in proper form with actual justification. Okay. Well, I feel like every time I say it, I sound very salty about the CS cohort and like the fact that they're not made to do this, but
it's okay. The only way, just show them how to do it.
Just show them how to. That's why my students in the CS cohort, I don't teach the entire cohort. I only teach a subset, right? And those that came to my class know that I do things this way, but the students that are not in my class don't. Yeah. I don't know if the TCX students will feel shortchanged because they're like, oh, how come the CS students get to do things so easy? And to me, it's like, oh, you have no idea, man. All the mistakes they make, like every time they hand wave something and they talk themselves into a circle, or like they make all these issues because they weren't following the rules, right? And it's because like when we are grading, the syllabus doesn't have rules. So then it's kind of like it becomes a game of like either I think it's correct or I think it's wrong, which is such an absolutely not the right way to do your assignments. Anyway, let's get into it.
Yes, let's get started.
Let's get started. Let's get started. So I want to prove that 2 is an irrational number. And so the first thing I'm gonna do is I'm gonna assume that root 2 is, well, okay, I guess I should write it this way. Should we okay, you know what? I'll write it this way. I'm gonna write it this way. I'm gonna say assume not the case that root 2 is in Q. Oh wait, sorry. Sorry. The initial statement is that root 2 is an irrational number. So what we need to
Yeah,
write,
I think you should write
assume.
down what statement you're trying to prove.
Oh yeah, okay. So we want to
somewhere.
show, so this is not want to sell. We want to show that square root 2 is not in the set Q.
Yeah.
Okay. So I'm going to assume that it is not the case that square root 2 is not in the set of Q. Okay. Well, I'm just gonna say this is logically equivalent, I suppose, to just saying that square root 2 is in Q. Okay, so this is just logically equivalent to line 1.
Yeah.
Now what I'm gonna do is I'm gonna actually apply lemma 2 right out the gate. I'm just gonna apply it. Okay, so I'm actually going to write root 2. Oh wait, sorry. I gotta do the rest of the statement. So I'm gonna write down. I'm gonna copy paste everything that exists onwards. So I'm gonna say exist P in Z. Okay, Q in Z. So now you're gonna see me shorthand a little bit, right? I'm gonna skip the exist here. Okay. For all D in Z. Okay, I'm gonna write down. I'm gonna copy paste everything, but wherever there is an X, right, I'm gonna swap it out for square root 2. So square root 2 is equals to P over Q, and Q not equals to 0, and divides. Some people can probably skip like ahead by 10 seconds and like might be safe. Might be quite safe.
Yeah,
And
you just copy exactly. Yeah.
divides dq implies, okay, that was a mouthful, d equals to 1.
Okay.
Right? Okay, so all I've done is copy paste this line. Okay. And I've swapped out. Okay, I guess I actually combined 2 rules into one. So to be very safe, I should have like probably copy paste the lemma first, right? So I'm gonna oh sorry. To be very safe. Wait, let me move my mouse properly. To be very safe, I'm going to actually do things step by step here. So I'm gonna copy this. I'm gonna move it down 1. Okay. So in other words, right, I caught myself skipping a step, actually. Right. So this line is correct, but before that, we need to have one more line where this is X. And I'm gonna move these I'm gonna move these to the right a little bit. And I'm going to just to the right a little bit, I guess here. And I'm going to write down for all X in Q. So I'm using the lemma. So I'm going to cite it, right? Because the lemma is here. I'm actually just going to cite it. I'm going to say I'm using lemma 2. I'm using lemma 2. Okay. And from lemma 2, I'm going to copy paste everything, right? Except I will replace X with square root 2. Right? So the rule that allows me to do this, universal instantiation. Right? We also need the fact that square root 2 is assumed to be in Q. So the rule again needs to take two lines, right? It needs to take line 2 and line 3. Exactly.
Mm-hmm.
Okay, let's keep going. So there's quite a few things to unpack here. So I'm gonna do the thing that you asked last video, right?
When you renumber your thing.
Yeah, 4, yes.
Yeah.
4. Okay, so what we're going to do, I'm going to compress this down a few lines so that the proof is a bit shorter. I'm going to let A be from Z and B be from Z such that, and again, I'm basically copy pasting these things, but I'm replacing P and Q for A and B, right? So now we're giving these values like names, right? So put this here. I gotta delete my squiggle. Okay, delete that too. So this A over B, right? And here we're saying that B is non-zero. And here we're saying that for all D, if D divides A and D divides B, then D is equals to 1. Right? So what we're doing here is that we are, again, instantiating the statement with P and Q, instantiating with variables A and B, like values A and B, right? So P and Q are variables, A and B are values, right? We're instantiating our variables with values. So we're replacing P and Q for A and B. Okay? So the next thing to do is probably to start using, like trying to do the very similar math that we did in the other proof, right? So from this line, we can start saying something about square root of 2. We can start saying that 2 must be equals to A squared over B squared. This is basic algebra from line 5, right? So sorry, I said B squared by root B squared, right? I'll do a few lines step by step for you. So now I can say 2B squared must be equals to A squared. Okay, so we know for a fact that A comes from Z. So it's okay for us to conclude that A squared must come from, do I want to say that? I probably want the other one. We know that B comes from Z. We know that B comes from Z. So we're going to say that B squared is from Z. Okay, so in particular, right, let's do a little bit of pattern matching here. I know that A squared is equals to 2B, and I know that B is an integer. So it is now safe for me to say exists a K in Z such that, oh, sorry, that's not such that A squared is equals to 2K. Okay, so this is our existential generalization. Okay.
Yeah, it'll come out eventually, but yes.
Oh yeah. So at this point, like if you watch the previous video, right, we and last week's videos, like I hope that you all kind
Wait,
of
your
like
numbering
roughly...
is weird. It should be line.
Oh yeah. Why did I say 7 and 8 again?
I don't know.
You're my manual proof checker today.
Yeah, it'd be better if we have an actual proof system.
Oh, waiting for someone's PhD to develop it.
Eventually.
I've already done my PhD and I finished it already, so I guess it has to be your PhD, huh? What a shame, what a shame. Okay, let's keep going, right? So we know for a fact that there is an integer that A squared is equals to 2K, which means that we can now say, by definition of even, we know this means that A squared is even. Okay, now I'm gonna, for the sake of time, because I don't think you all want to see me copy pasting this directly. I'm as in handwriting it. I'm just gonna copy paste it. Okay, so
nice.
what, this is genius, no? I find I see this as an absolute win. We're using actual digital technology, wow, technology, right? So okay, so this is using lemma 1. We're using lemma 1 now. So lemma 1 says that for any integers, if the square of the integer is even, it must be even too, right? Okay, so let's see. A comes from the set of integers, right? On line 5, we said that. So now what we can say is that A squared must be an integer. So this is basic algebra. Okay, let's keep going. So since A squared is an integer, right, I can now take this line and create a statement, right? So the statement I can create would be even A squared implies even A, right? So how do I get here? This is universal instantiation on line 11, right? Oh, and line 12, I almost forgot that you're supposed to use 2 lines, but line 11 and line 12.
Oh,
Okay. And then now I can take this line and apply modus ponens, right? And conclude that this means that that A is even. So I'll say even A. Okay. So so we've gotten to the next thing, which says that A is even. Okay. So what does it mean when A is even? Well, then I can say this must mean that there is an integer k in Z such that A is equals to 2k. Okay. So wow, the rules the rules are like wow amazing. This is if
yeah.
only this was like an AI or like a machine, like a computer doing it, it'd
Yeah,
be
that
so
would be cool though.
impressive.
Like it
That'd be
just
very cool,
derives
right?
the rules for you.
Yeah, it just
Yeah.
derives the rules for you. Yeah, but sadly we can't have that.
Ah,
Yeah.
sadly.
Okay, so we know there's an integer k that happens so that A is equals to 2k. So I'm gonna say let t be such an integer. Let t be the integer. We'll give it a name. Let t be such that A is equals to 2t. Okay. Let's keep going. So because of this, right, what we can now say is that if we go back and refer to the math, right, okay, we know that 2b squared is equals to a squared. So 2b squared equals to a squared. This is from before, is now equals to 2 times 2t squared. So this is basic algebra.
Mhm.
Okay. And let's keep going. So this means, right? So let's check this out, right? So since t is an integer, it must mean that 2t squared is also an integer. Okay, so this is basic algebra again. Okay, well, I have an integer and I have that 2b squared is equals to 2 times this thing, which is an integer. Okay, so what this also means mathematically is that b squared is equals to, oh, this is not the one that we want, right? But I guess I'll just write it anyway. So now this is equals to 2t squared. So just again, this is basic algebra. This line is
Mhm.
extra. We don't need it. But as you can see, in the middle of a proof, sometimes you do write extra lines. Like it happens so often, right? Okay, but now this is the important one, right? So since t is an integer, we can also say that t squared is an integer. Okay. So this is also basic algebra. So now, right, b squared is equals to 2 times an integer. Okay, so what does this mean? This means that there exists an integer k such that b squared is equals to 2k. Okay, which means that b squared is even. Okay, this is the definition of even, right? The rules are being filled out, right? So like look,
Yeah.
every line justified. Every take
Uh,
notes, CS students. Take notes, CS students. Every line justified. Yeah.
it's super tedious though. Like
Hey, no
even the
complaints.
smallest thing.
Even the smallest
Yeah.
things. Yeah, because this is how you prevent mistakes, right? That's what I would say.
Right.
Oh, what just happened?
No, it's okay. I just dragged the
Yeah,
line, but
like okay, look,
mm,
I okay, like, in the middle of the proof, I'll tell you, I agree it's tedious. I agree it's a lot of lines, right?
yeah.
But I would still prefer someone does this so they don't make mistakes in their proofs.
Mhm,
Like
mhm.
you're wrong if you join me in TAing CS12C1S, right? The CS undergraduate discrete math module, I swear you'll look at so many proofs, right? Well, quote unquote proofs, right? And you have to grade them wrong, but you cannot. You cannot because intuitively it's true, what? And then it's like, ah, like you know what I mean? There's no solid grading criteria. It becomes a game of
I've
like
never
I say
graded
it's
proofs
correct or I
before,
say it's
so
wrong. Sorry?
yeah. No, I've never graded proofs
You've never
before,
graded proofs
so
for, yeah,
yeah.
trust me. You don't want a math module, right, to be a case of it's correct or wrong because the prof said so or because the TA said so. That's not objective. You know what I mean?
Mhm, mhm.
Yeah. Let's keep going. So so it's so b squared here happens to be even, right? And if we remember, I'm actually going to copy paste it this time, right?
Uh-huh.
Using the same lemma, right? I can now say a very similar statement, I can now say even b squared. Actually, you know what? At this juncture, I think, right, like you all should probably like
Yeah.
open up the notes so that you can see the whole proof while I annotate it for you guys. Because maybe, but everything is done step by step. Everything is done step by step. Right. So again, we use the lemma, and this time around, we instantiate the lemma with variable with value b instead of value a. Okay. So we're gonna do Yong's favorite again. Right.
Yeah,
We'll do
most
modus ponens
opponents.
now. I don't think it's a cool name, but anyway. So now we can say even b. Right. It's just modus ponens.
Yeah.
Okay. And let's keep going. So now b is even, a is even, right? So just remember, b is even, a is even. Okay. So what we can say is that there exists a k in Z such that b is equals to 2k. This is the definition of even, right? And now what we're going to say is what variable should I use? S. Let S be in Z such that such that b is equals to 2s. Okay. So in particular, we know that b is equals to 2s. Okay. We also know that a is equals to, let's see, a is equals to 2t, right? That's what we wrote just now. So I'm going to say a and a is equals to 2t. I don't actually think I need to write this, but I guess I'll do it. Okay. So now by basic algebra, I know that 2, wait, let me write it this way. By basic algebra, I know that 2 divides A and 2 divides B. Okay. I also know for a fact that 2 is not equals to 1. Okay. In fact, let's be very careful here. I'm going to write it this way. We're very close. I don't know if you all can see how we're supposed to derive the contradiction yet, but of course we need to now somehow find a way to say that 2 is equals to 1, right? So let's go back and see where something might be relevant for us to do that. We want to find a way to say 2 is equals to 1. Okay, we want to find a way to say 2 is equals to 1. Oh, let's look at line 5, right? So what does line 5 say? Right? So line 5 says, okay, oh, we're missing something, right? Where's the for all? Oh yeah, no, sorry, not line 5, line 4, line 4. We want to look at line 4, right? So what does line 4 say? Well, line 4 says, right, that, oh, no, we copy pasted this wrongly. Someone should have stopped me, right? So let A and B be such that, be such that for all D in Z, right, then all this is true, right? Okay, so A and B were values such that this statement held, right? For all D in Z, divides dA and divides dB implies that D is equals to 1. Okay, so how do we write this now? Well, the next thing we're going to say, okay, is that 2 is an integer. This is basic algebra. I think we can agree, right? 2 is an integer, right? That's very non-controversial here.
Yeah.
Okay, so now what we can say is that, well, since 2 is an integer, we can now instantiate the for all statement and say divides 2a, divides 2a and divides 2b implies 2 is equals to 1. So while Yorong fills that rule out, right? How did we get here, right? How did we get here? Well, we got here because we took this line, this for all statement, and we instantiated it with the value of d being equals to 2. Right? So we're doing, again, universal instantiation. Okay, so we're so close, like it's right there. It's really right there, right? So what should we do? Well, take this line and apply modus ponens, right? Modus ponens. So you apply modus ponens, right? Look, condition fulfilled, right? So now we will say 2 equals to 1. Okay, so close, right? So the next line will say, right, that 2 equals to 1 and not 2 equals to 1. Okay, so this is conjunction. We're just conjuncting these two lines, right? We're conjuncting lines 29 and 32. Okay, we're there. We're basically there. Contradiction. So right, so we're using the contradiction rule. We derive the statement and we derive the negation of the statement. So contradiction rule, we get that's my crappy rendition of a trumpet, a fanfare trumpet, but we get the contradiction rule. Okay, so we have a contradiction, right? So where did we go wrong, right? In other words, contradiction means that we went wrong somewhere, right? Somehow we proved that 2 is equals to 1, but obviously that's not true, right? So where did we go wrong? Let's scroll back, right? Scroll. Aha! Very first line. We assumed that it is not the case that square root of 2 is not a rational number. Right? So what we now do is copy paste this thing without the negation symbol. Paste it here. And write 35. Ta-da! Proof over. Proof done. Right? So the last rule that we're missing is the proof by contradiction rule. Right? So proof by contradiction rule on lines 1 and 34. That's how you do a proof. This is a formal proof system. Well, not really formal proof system, I guess, but it's like a formal proof system, semi-formal proof system.
Oh, it's more rigorous than whatever you wrote.
On the notes, is it?
No, as in the sketch that you give.
Oh,
in
the sketch I gave, right?
Yeah.
Yeah. What is this? Look, I like what is this? This feels. You know what this feels like? This feels like one ply toilet paper.
What?
The argument is so thin I can see through it. This feels like reinforced, like, like 4-ply. You know, 4-ply is a thing now. I never knew that 4-ply toilet paper was a thing, but they're making 4-ply toilet paper now. I'm just like,
Right.
I don't even think my kitchen towel was 4-ply, man. Like, do I really need 4-ply toilet paper? Right? I don't know. But my point is, like, we're not kidding, right? Every line is justified. Every line is justified. This means that you can check your proofs for yourself, This is the equivalent of teach a man to fish. But instead it's teach a man to do proofs. Right?
Mhm.
Like, yeah. So now you can check. Every line has to be justified. Every line, right, has to literally have one of these tags, right? And you can check that it's correct. So if there is a line that cannot be tagged, right, the proof is considered wrong, actually, right? You can imagine how with this, right, people just write random stuff and then it's like, is it correct? Is it wrong? Like, who's the arbiter, right? Who's the arbiter of truth here? Is it you? Is it me? Is it Yongrong? Right? Like, it shouldn't be anyone, right? Like, there is no arbiter in this proof. I know. I have an agenda that I'm going on, and the poor students have to hear me talk about it. But I really think, right, the fact that you can do this means that you don't have to keep asking me, Prof, is my proof correct? Is my proof wrong? You don't need to know that. Like, you can just check the notes. Like, if you follow these rules, right, it will pretty much tell you. It's like playing chess. You can play chess by yourself, really, because you know the rules of chess, right? It's written down somewhere. Yeah, exactly. It's universal. So this is how proofs work. Right? So this is proof by contradiction. Like, okay, I know, very, very, very scary, right? All I can say is TLDR. The moment you get one of these, you can create one of these. The moment you can create one of these, right, you're done. That's the idea. Yeah. Any final remarks for this section,
No, just all the best. All the best to the students that needs to write proofs.
Hey, don't make it sound that bad. We won't. Okay, I don't think I'll give them something this long. I don't think I'll ever ask them to prove like square root of 2 is irrational. You know what I mean?
Okay.
But maybe we can get them to prove square root of 3 is irrational. Because it feels like you should just take inspiration from this proof, right? You know what I mean?
Yeah, I mean, I'll just replace 2 with 3 and then see
and see what happens, right?
Yeah.
And actually, that would actually be very interesting. I've never seen a proof of whether square root of 3 is irrational or not, right? So maybe it's worth looking into. Like, see whether you can try to substitute the same proof, the same template, right? But you try to put 3 in here and see how everything changes and see whether you can still prove that 3 is irrational. That would actually be very interesting. No? I think that would be very interesting.
I think it'll be
Okay.
very hard too.
You think it'd be very hard? But I mean, we did the proof for them already. So all they have to do is kind of like see what changes, right? You know what I mean?
Uh-huh.
But I guess now you cannot use the fact that every number is even or odd or this squaring thing. You might have to change that for another theory. Like this one might break,
Yeah.
right? This thing might break
Yeah.
because it's not about even or oddness anymore. It's potentially
The mod
something
mod
else.
3.
Yeah, you have to do mod 3 now. Okay, so it might be still quite complicated. Yeah, but okay. So that's all we have for you in this video. See you in the next one.